This is 2018 AIME 2 problem number 14, and we have already provided a non-projective proof for this problem, and this is a second solution where we provide a projective solution actually. So let me repeat the question. So we're given an incircle omega which touches the triangle ABC on side BC at point X. Here you can clearly see it. AX hits the incircle also at the point Y, and at point Y we draw a tangent to omega and we let it hit AB at P and AC at Q. We are given some length relationships and we want to find AQ, basically the length AQ. Okay, so the main claim, the kind of the crux move of the projective solution is to observe that if you name these as M and N, that the diagonals of quadrilateral PQCB will meet on AX. Okay, so let me repeat that. So we have a circumscribed quadrilateral PQCB with W as the circle inscribed in it. Right, so I claim, and I will just prove it in a minute, that if I extend these diagonals, they will meet at on AX and on MN as well, by the way. Right, so all these lines are concurrent. Okay, so and they will concur at this point here. Let me go ahead and prove it quickly. So let me create a new shape, I would say, and then based on that new shape, let's see if we can discover more facts about this nice result. So what's a natural way to construct this quadrilateral? So we can start with a quadrilateral inscribed in a circle, and from there we will naturally create a circumscribed quadrilateral like PQCB here. Okay, so consider this one for example. So we have these points, and maybe I can take this point here, and I don't know, maybe this one. Okay, so we have this quadrilateral which is inscribed in a circle. Let's name it as A, B, C, D. And at this point, I go ahead and draw the tangents to these vertices. So I'll go ahead and do that. So the tangents are like that. Here is one intersection point. I draw another tangent here, and they will probably intersect right here, and one more. We let it intersect with this one. Yeah, just here actually. I don't have to go too far. And finally, this one here. Okay, so let's label these points probably as, well, why not? A prime, B prime, C prime, and D prime. I will finally draw four more lines probably, and here are the interesting lines, right? So consider, for instance, let me go ahead and draw these diagonals of the inscribed quadrilateral, right? So quadrilateral ABCD, remember, is inscribed in a circle. Oops. Okay, there we go. And we let it intersect. We let these diagonals intersect, say, at point P. Let me actually make the picture slightly larger. Okay, good. So let's see how far we can exploit this picture. Oh, and before I do so, let me go ahead and extend two more things. Let me go ahead and extend these lines first, and I would let them intersect, say, at the point, say, K. And, oh shoot, AB and CD look very parallel, huh? That wasn't my intention. They will intersect someplace. Let's pretend they will intersect somewhere over there. At a point far from here, say they intersect at the point M. Okay, so these two lines meet somewhere far at the point M. Okay, quick things. We have ABCD, which is our cyclic quadrilateral ABCD, and we know from Brocard theorem, for example, Brocard, let me write that down. So from Brocard theorem, we know that the polar of P is the line Km. Does that make sense? So Km is indeed the polar of P. And in a similar way, for instance, Kp is the polar of M. Okay, let's write that down. Kp is the polar of M. Actually, this one was a better one. Okay, good. So we have that for now. Let's see. So Kp is the polar of M, and for instance, you can use Lahire's theorem to show that. Let's just keep it as such for now. Right. Okay. The polar of B prime, on the other hand, is the line BC, which also goes through A, by the way. So BC is the polar of B prime, right? So B prime, the perpendicular, the polar of B prime is the line BC, which contains K, by the way. K is on this line, right? That makes perfect. I mean, this is super cool. And one more, D prime, the polar of D prime is AD, which contains K as well. Okay, so there you go. Okay, AD, the polar of AD is, the polar of D prime is AD, right? Yes. And it certainly contains K as well. So now when you combine these three results, we just realize that the polar of M, B prime, D prime, they all go through the point K, suggesting that M, B prime, and D prime, and the polar of P as well, sorry. That one as well. So look at these 4 points. So these 4 points, all of their polars go through the point K. So that would suggest that there's only one explanation, and it is that these 4 points are indeed collinear. That's really cool now. Maybe I should use a different color, say black. So we have this really awesome line. Oops, something like, okay, so this one goes to the point M also. That's pretty cool. So you can make a similar argument and show that the polar of A prime, P, C prime, and K, they all go through the point M. As a result, these 4 points has got to be collinear, right? Because all of them are on the polar of M, and if you have 4 points all on the polar of M, and the polar of M is obviously a straight line, so therefore these 4 points are collinear as well. And that kind of nicely proves the desired, this is a general result that you can easily apply to our situation, which is the same thing, right? So does that make sense? The only thing which was disturbing for some of you was probably to use Brocard theorem to prove the very first one. The others are kind of more well-known results, and to prove this result, you can use perspectivity, for instance, or cross ratios. And so I'll just leave it to you as an exercise, let's say, right? So this is one proof, and you can also prove this result very neatly using what? Briançon theorem. Let's provide another one. So if you have a circle or any other conic section for that matter, and to that circle you draw some tangent lines like this one. So there's a tangent here, there's another one here, a third one, say here, 1, 2, 3, so I need a fourth one. right here, a fifth one, and finally number 6, say, oops, like here. Awesome. So this is so if you have a hexagon which have an inscribed circle, and now we can use Briançon theorem, which happens to be, by the way, a dual of Pascal theorem. These if I connect the diagonals of this hexagon, well, the opposite pair of vertices of this hexagon, boom, they intersect at one point, and this is a Briançon. Again, you can use poles and polars to establish that, but this point is not necessarily the center of that circle, right? So the center of the circle is somewhere else, but they meet at one point. So how does this relate to this previous result that we have just found? If you focus here, all you do really is you collapse two of the sides, basically. So if I collapse this side and I virtually make it a single point, and I do the same thing for another side, and boom, that will give me the desired result, right? So for instance, let me quickly go ahead and do that. If you have a circle and you draw instead 4 tangents, so 1, 2, maybe 3, and 4. There you go, 4. Now I will apply Briançon theorem twice. Well, I need to first label some of these points. Come on. Oops, okay, my computer is okay. So there you go. So let's go ahead and label these points. So let's label this the vertices here as A, B, C, D, and these touch points as E, F, G, H. Now we will apply Briançon in this following way. I will apply it to to the following hexagon, namely hexagon A, E, B, C, G, D. Now this is a strange hexagon, isn't it? Because look at these sides. AE and EB are it's just a straight line, right? So so I'm splitting AB. I'm reinterpreting the side AB of this quadrilateral, this circumscribed quadrilateral, as 2 different segments, right? Does that make sense? And as such, now I can apply a Briançon to these 6 points. So opposite vertices, they all meet, right? So boom. But then I can reinterpret this picture in the following way. Consider this time instead the hexagon BF, C, D, H, A. And now the vertices are, let me label them like this. So the vertices, this time we still have these 4 vertices, but now we have 2 more here. This is the interpretation. Now what will happen to the diagonals? So applying Briançon, the diagonals now will be this diagonal. Well, okay, so before I draw that one, 2 of the diagonals are still AC and BD, right? So AC and BD are the red ones, and the third one should go through that point as well. And boom, now you have all 4 segments meeting at this midpoint here, at this point here, sorry. They all concur at that point. Okay, going back all the way to our original picture, and maybe let's make it 100% again. Okay, now it makes perfect sense that you have the circumscribed quadrilateral PQCB, and as such PC, QB, MN, and YX, they all concur at this point. Let's call this point, for example, as P. And now I can go ahead and use some let's see. Okay, so let's use some projective techniques now. One idea is let me see. Yes. One of the standard configurations is that you can extend PQ and you would let it meet BC like that. Say it meets at the point R. It turns out that I claim MN will also go through that point R. Do you see why? You can clearly observe it from the following reasoning. Well, yeah. Yeah, so the reason it happens is because look at the point R. Where is the polar of this point? The polar of R is clearly, the way to find the polar is obviously you draw the tangents from R to that incircle omega, and the tangency points are X and Y, and XY is the polar of R, right? So the polar of R is equal to xy, but xy contains the point A. So A is on the polar of R, suggesting by Lahire theorem that the polar of A indeed goes through that point R, right? But the polar of A is Mn, right? So therefore Mn should contain the point R, and boom. So therefore this implies that M and R are collinear. Okay, so perfect. And well, yeah, okay, so let's not speculate further, but yeah, we have some really nice symmetry in this picture and nice construction in this picture. But why did we do that? Because it turns out that one of the well-known configurations tells us that the cross ratio of, for instance, points Rx and BC, the cross ratio of Rx, BC is -1, right? And similarly, for instance, the cross ratio of, I can say, for instance, ANQC is -1 as well. I think the one that I will be using will be APXY. Does that make sense? So this cross ratio is -1 as well, and this just follows from perspectivity with respect to point R, right? Does that make sense? So let's first write that down. So it's well known that the cross ratio of AN QC is equal to -1, but then taking perspectivity with respect to point R now and projecting these 4 points onto the line AX, we just realize that we have AP and YX. Yes. So what we did is we projected these 4 points A and QC onto the line AX, and with respect to the perspectivity from point R. Okay, now let's go ahead and right. Let's take one more perspectivity actually. We can also take perspectivity, say with respect to yes, again with respect to point R, but this time onto line AB, okay? And so therefore this would be, and Y would go to P, well, A remains, P goes, oh my, oh, I just didn't realize that there are 2 points P's here. Oh my god. Okay, so sorry for that. So let's call this point as O. Now O is the center of the circle. PQRS. Okay, sorry for that. Really apologize for that. So this point here is S. So so ANQC AS. So this is an S. And finally AM. So AS is going to AM. And we have YX, Y is going to P, and X is going to B. Okay, there you go. Whew. Okay, now finally we can go ahead and apply the definition of the cross ratio. So we can start with the cross ratio here, and then we can also check this one. Okay, and that should give us the result immediately, hopefully, if we do the algebra properly. Let's go ahead and do that. let me use a different color. Okay, so let's start with A and QC being equal to 1, right? So we have a 1, well, in absolute values, obviously, is equal to, so it is just QA over QN. So yeah, so let's write that down. QA over QN divided by CA over CN, right? So CA over CN, and I can just write it as well, yeah, so let's write it as QA over QN times CN over CA. Well, actually, I should have started from the other one because the question is asking for QA. Okay, let's go back to this this ratio. Actually, let's just fit it in here. So 1 is equal to, let's do it again, PA over PM, PA over PM divided by BA over BM, BA over BM. That's the definition of the cross ratio. So therefore we have PA over PM times BM over BA. Okay, so PA is given in the problem, I believe, as 3. PM is yeah, well, we can keep it as PM, I guess. BM is also not known, so let's just keep it as well. And finally, BA. BA, we know it's 3 plus 4 is 7. So you might say, hey, how does this finish, right? So from here, we get that, so this implies that 3BM, cross multiplication, is equal to 7PM. However, BM plus PM is just equal to 4, right? So for that reason, yes, because yeah, it's given in the problem that it's equal to 4. So all you need is now solve these two, and knowing that BM plus PM is equal to 4, if you solve it like we did in our first solution, you will get that PM comes out as 6 over 5, and from there you can also get BM as 14 over 5, I believe. Yes. Okay, so now finally we can plug it into this expression now. So we have QA is the desired distance. And obviously, like we did in our first solution, AM is equal to AN because of equal tangents. So so we have well, okay, so let's just keep it for now. QN over, so this one is CN over CA is 8, right? Does that make sense? But because AN is 3 plus 6 over 5, this one is also 3 plus 6 over 5, which is 1521 over 5, right? Does that make sense? Oh, well, it was 21 over 5. So therefore, the remaining distance would be just 8 minus 21 over 5, or 40 minus 21 over 5, 19 over 5, right? So therefore, NC is 19 over 5. Let's just write it like this, 19 over 5. But if I know NC, yes, so the desired distance is AQ is X, so therefore QN itself would be just 21 over 5 minus X, right? So yes, or minus X. So therefore, we have here 21 over 5 minus QA, and boom, that's it. So we have found, so 1 is equal to this ratio, and from here you can easily calculate QA as I believe 168 divided by 59. Obviously this this projective solution is well, you can come up with this solution during the exam if you know the configuration, if you've previously seen this type of configuration. If you haven't, then obviously our other solution would be the way to proceed. And that's all for this problem, and hope to see you guys in our next lecture.